Hi everyone, a warm welcome to the fifth part of problems in Lagrange's equation PP plus QQ equal to R. I explained the method for solving this equation in the suggested video. Its auxiliary equations are dx by p is equal to dy by q is equal to dz by r. Firstly, try to find two solutions of the auxiliary equation. Really, there are two methods for solving the auxiliary equation: grouping method, method of multipliers. In this video, I am going to solve a few problems in which both grouping and multiplier technique are applicable. If u equal to c1 and v equal to c2 are two solutions of the auxiliary equation, then f of uv equal to 0 is a solution of the Lagrange's equation. Also remember, f of uv equal to 0 can also be expressed as u equal to phi of v. Let me start.
We have to solve an important question. Z into x plus y p plus z into x minus y q is equal to x square plus y square. You compare the given equation with the pp plus qq equal to r. Then what is p? P is z into x plus y. What is q? Z into x minus y. What is r? X square plus y square. You write our auxiliary equation. Our auxiliary equation is dx by p is equal to dy by q is equal to dz by r. That is dx by z into x plus y. You put p, q and r. Next you find two solutions of the auxiliary equation either by grouping or by multiplier technique or by both. See, by looking into the auxiliary equations, here we can find one solution by grouping by considering first two ratios. See, this implies dx by, see in these two ratios you can remove z. So this implies dx by x plus y is equal to dy by x minus y. Next, you cross multiply. You can see this x minus y into dx is equal to x plus y into dy. You take the right side to the left side. X minus y into dx minus of x plus y dy. You open the bracket, which implies x dx minus y dx minus x dy minus y dy is equal to 0. So when you take this term to the left side, you can see now right side is 0. Now is it in separable form? No. Here the first and last terms are in separable form, but the middle two terms are not in separable form. But here we can rearrange it for suitable integration. Really, we can't separate the variables here. Here you watch the method for integration. See, this implies x dx. You take a negative sign, common outside. So y dx plus x dy. Really, we can't separate the variables, but we will apply another technique for solving the differential equation. The last term is in separable form. So, see, finally the solution of the differential equation is obtained by integrating. So, you have to make this term for integration. See, it is ready for integration. This is also ready for integration. See how the middle two terms are rearranged for suitable integration. See, y dx plus x dy is always d of xy. You have to remember that. What is d of xy? D of xy is x dy plus y dx. So whenever you see such a sum, you express it as d of xy. So it is this minus y dy equal to 0. Now it's ready for integration. So integral x dx minus integral d of xy minus integral y dy is equal to a constant c1. What is integral x? It is x square by 2 minus. What is integral d of xy? We know integral integration and differentiation are reverse process each other, so this will cancel and the middle term is xy. That is integral of d of xy is xy. What is integral dx? Integral dx is x. Similarly, what is integral d of xy? It is xy minus y square by 2 equal to z1. You can take 2 LCM. So x square minus 2xy minus y square equal to 2c1. Since c1 is arbitrary, you take it as c1. So this is one solution of the auxiliary equation. Next, we have to find one more solution of the auxiliary equation. But we can find another solution by grouping. But you can find a solution by multiplier technique. See, can you try to find a combination in which the denominator is 0? If you take this combination, that is x dx minus y dy minus z dz, then we can see the denominator combination is also 0. So that is zx into x plus y minus y z into x minus y minus z into x square plus y square. If you open the bracket and expand it, we can say like terms will cancel each other and the denominator is 0. So this implies the denominator is 0. In multiplier technique, this implies x dx minus y dy minus z dz equal to 0. See, it is in variable separable form, so its solution is given by integral x dx minus integral y dy minus integral z dz is equal to another constant c2, which implies x square by 2 minus y square by 2 minus z square by 2 equal to c2. You take 2 LCM, you can see it is x square minus y square minus z square equal to 2. See, this is another solution of the auxiliary equation. Now we have two solutions for the auxiliary equation. So we can write a solution of the partial differential equation. And the solution of the partial differential equation is f of, see, previously we got one solution, that is, what is that? X square minus 2xy plus y square, comma, x square minus y square minus z square equal to 0. So one solution of the partial differential equation is f of, previously we got x square minus 6y minus y square equal to 0, comma, x square minus y square minus z square equal to. Next we have to solve another interesting partial differential equation. Z square minus 2xy minus y square into p plus xy plus xz into q is equal to xy minus zx. First you compare this equation with the Lagrange's equation. Here p is z square minus 2zy minus y square. Q, what is q? It is the coefficient of small q. What is r? It is the right side, which is free from p and q. Next, what is its auxiliary equation? dx by p is equal to dy by q is equal to dz by r. This implies dx by z square minus 2zy minus y square is equal to dy by xy plus xz is equal to dz by xy minus zx. Next, we have to find two solutions of the auxiliary equation, either by grouping or by multiplier technique or by both. See, here you can find a solution by grouping. See, here you look at second and third ratios. Here you can take a common factor x. Similarly, a common factor x in the denominator, you can cancel the x. Then the denominator is y plus z and here it is y minus z. So there is a possibility for separating the variables. So we will try. So this implies dy by x into y plus z. We are taking the last two quotients, ratios. x into y minus z. See, x will cancel, so this implies dy by y plus z is equal to dz by y minus z. This implies you cross multiply. That is y minus z into dy is equal to y plus z into dz. You take this to the left side. So y dy minus z dy minus y dz minus z dz is equal to 0. Here, first and last terms are in separable form. It's similar to the previous equation. So y dy, here you take a negative common. So you can see it is z dy plus y dz minus z dz is equal to 0. See, that is y dy minus of this d of yz minus z dz. Now it's ready for integration. So this implies integral y dy minus integral d of yz minus integral z dz is equal to c1. See here, right side is 0 and integral of the constant is a constant. Integral of the constant 0 is a constant. See, what is its integral? Y square by 2 minus yz minus z square by 2 equal to c1. That is y square minus 2yz minus z square equal to c1. See, this is one solution. Next, we have to find one more solution for the auxiliary equation, but it's not very easy. Here, it's too difficult by grouping method, but you can find one solution by multiplier technique. So, you have to find a combination in such a way that its denominator is 0. You can easily find such combinations only through practice. See, here the suitable solution is, if you take x dx plus y dy plus z dz, then what is the denominator? X into z square minus 2zy minus y square plus y into xy plus xz plus z into xy minus zx. You open the bracket and simplify. You can see each term cancel each other. And the denominator is 0. That is x dx plus y dy plus z dz by 0. This implies x dx plus y dy plus z dz equal to 0. See, now in variable separable form, so its solution is by integration. So integral x dx, integral y dy, integral z dz is equal to c1. So which implies x square by 2 plus y square by 2 plus z square by 2 is equal to c1. That is x square plus y square plus z square equal to, see, in the previous solution we have taken the constant as c1, so here you have to take it as c2. So c2. So this is another solution. We have two solutions of the auxiliary equations. Y square minus 2yz minus z square equal to c1 and x square plus y square plus z square equal to c2. So we can easily write the solution of the given partial differential equation as f of y square minus 2yz minus z square x square plus y square plus z square equal to 0. Or you can write it as y square minus 2yz minus z square is a function of x square plus y square plus z square. Next we have to solve another partial differential equation z into xp minus yq is equal to y square minus x square. Here we have to write p. P is the coefficient of p. See, you can rearrange this equation as zxp minus zyq is equal to y square minus x square. So what is p? Zx. What is q? Minus zy. What is r? Y square minus x square. What is our auxiliary equation? Dx by p is equal to dy by q is equal to dz by r. This implies implies dx by zx equal to dy by minus zy is equal to dz by y square minus x square. See, by looking into the auxiliary equation, you can easily find two ratios in such a way that grouping method is possible. Can you find it? Yes. See, you consider these two ratios. See here, z will cancel. Then it becomes dx by x is equal to minus dy by y. It is in variable separable form, so you can integrate it. So integral dx by x equal to minus integral dy by y plus c1. See, this implies, what is integral 1 by x? This implies log x is equal to minus log y. See, these terms are in terms of logarithm. So you take c1 as log c1, which implies log x plus log y is equal to log c1. That is log xy equal to log c1, which implies xy equal to c1. So we have one solution, xy equal to c1. Again, we have to find one more solution for the auxiliary equation, but it's too difficult for finding a solution again by grouping method. So you try to find a solution by multiplier method. For that, here you have to take the combination as x dx plus y dy plus z dz. So this implies denominator is x square z minus z y square plus z y square minus z x square. If you take this combination, you can see the denominator is 0. So this implies x dx plus y dy plus z dz by 0. This implies, by Lagrange multiplier technique, numerator is 0. See, it is in variable separable form, so we can integrate it. Integral x dx plus integral y dy plus integral z dz is equal to c2. That is x square by 2 plus y square by 2 plus z square by 2 equal to c2. That is x square plus y square plus z square equal to c2. See, this is another solution. So now we have two solutions. So we can write a solution of the given partial differential equation as f of xy comma x square plus y square plus z square equal to, or you can write it as x square plus y square plus z square as a function of xy, or xy is a function of by x square plus y square plus